Yes, please go ahead with your presentation now. Thank you.
Can you see the slides? Is it full screen?
Yes.
Okay. Okay. Well, thank you very much. It's always good to see you guys here. Another year. So I'm here for presenting a new paper related to reinforcement learning. And basically what I'm trying to do, I'm trying to model and capture the effect of partner selection strategies on the emergence of cooperation. This is a joint work between me and my supervisor, uh, uh, Professor Eric Powell, who is a group leader at CWI, Center for Informatic and Computer Science in Amsterdam. Well, I think, like always, there are some slides we're going to see related to our research question, the background, methodology, and experimental result. So I think there is not a better way by saying that I think at the micro level, it is very important. I think at the micro level, it is obvious that people, when it comes to cooperating with each other, people can follow a cooperative or non-cooperative behavior. So, and it's just because, you know, this options of choice that they have. So we cannot force them to always show a cooperative behavior with each other. But what is interesting is that at the macro level, usually if we encourage people to cooperate with each other within a team setting, this will result in social benefits. So the outcome is something positive. You can imagine, for example, when we are bringing a new employee to an organization, the knowledge of this employee belongs to himself or herself. But the moment we are encouraging them to work together with other team members, knowledge transfer can happen, and this will result into something very positive. Any system owner in general, it is in its interest to encourage people to collaborate with each other than compete with one another. But the problem here is that in general, modeling the cooperative behavior of a population is a hard problem. And the reason is, in general, identifying the motivation which fosters this behavior is difficult. It is very difficult to observe how this cooperation will propagate through the population and what conditions may stop this process from happening. So, but when we look at the literature, we see that usually there are two lines of research. Sometimes they're combined, sometimes no. So the first area, they try to bring or design some explicit agent motivation into the model. And a group, usually a group of researchers usually show interest in imitation dynamics, and other groups of researchers show interest in aspiration-driven dynamics. The first category, in imitation dynamics, we assume that an agent or a person, whatever the entity, I think in our case, it's more, we're talking about humans. So humans try to have an understanding of their surrounding environment. They can observe the environment. They can see what's going on there, and they imitate what other people are doing. And usually, if you, for example, consider in terms of reputation mechanism, we can argue that, yeah, we look at our surroundings, we see that who is the most successful one, and then we copy that person. So this strategy usually is called imitation dynamics. But for aspiration driven dynamics, we basically focus more on the individual level, and we say, well, people have some expectations, and whenever their expectations are fulfilled, they cooperate. If they have some expectations and they are not happy with the outcome of the collaboration, then this will negatively impact their experience, and the propensity of cooperation will go down. So these researchers, well, they are designing their model based on this idea. So aspiration-driven dynamics in general is very simple, not simple in the sense that basically you don't need to have some global information about your environment. So some researchers, they think it's a very big heuristic if we assume that who is doing better, and if we have access to the strategy of others. But in aspiration-driven dynamic, it's about you, and you play the game. If you are happy, you cooperate. If you're not happy, it will affect your experience, and probably you will change your strategy. So this is one aspect for bringing the motivation for cooperation or defection. And also there is another line of research which argues that we are not alone. So it's not about me and you playing with each other. It's about basically a network of people being together. And I think this is very reasonable in the sense that within a team also, we are dealing with a group of people, and these people are interacting with each other. So we are not isolated. So researchers try to bring this social connectedness and also capture the effect of this underlying network structure. And one more issue here is that when we are considering a network structure for this under like the model which you're building. So if you bring that network structure, so the question is, how do you want to select the other person that you want to interact with? So you have a choice, and we need to model that. And there are different, I think, algorithms in the literature based on entropy, based on evolutionary algorithms, based on some reinforcement learning. But in this research, we are trying to bring these three aspects together. So there are some research which has been done in the aspiration level dynamics. There are some researches which are done in the networking structure, but maybe networking structure plus the imitation dynamics. So we are trying to collect these three together. And also, when it comes to partner selection strategies, we were trying to use reinforcement learning, specifically banded learning algorithms, so that we design a pool of possible behaviors for each agent while they are playing game. And for the game itself, since the focus of literature mostly is on prisoner's dilemma game, so we also focused on this game specifically. And in terms of exchange of economic values with each other. So then when we are doing our simulation, we are interested to see the obviously the level of cooperation and its variation in terms of the median and interquartile range while the simulation is going on. So if we do that, the objective would be, well, we are designing a nice framework. We can consider the economic behavior of the agents while they are interacting with each other. So there is like a give and take. And then we also have a social system to show the networking structure. And well, this in its own turn can help us to see what type of setting of with what type of settings, which settings of the game can help us to generate a higher level of cooperation among the population. So, and the insight can help us to guide and regulate the evolution of cooperative behavior, which is something very appealing. So regarding the methodologies, I think you have an idea here. So we are going to do agent-based modeling. So we're targeting a system here. So it's about a group of people. They plan to cooperate with each other. We need to go for agent-based modeling because, you know, they are taking individual decisions. But the thing is the grid structure is putting some limitation in terms of connectivity with each other. So we have to bring the networking in. So we are borrowing different kinds of network from the networking theory with different characteristics into our agent-based model. And the last thing is this interaction, which I discussed, that we plan to use game theory or prisoner's dilemma for this purpose. So in our simulation, well, we have 100 nodes with fixed number of edges between them, 200 edges. We have 9 different networking topology. And you know, they are different in the sense that in some of them you can observe a very long diameter. So the network itself is very long, and there's a huge distance from one node to probably reach other nodes in the network. And also sometimes you see clustering coefficients, so you see groups of clusters among the individuals. So as you can see, the density of all these 9 networks are the same, and the only difference is the difference in the average shortest path length, the clustering coefficient, which we can consider them as some kind of local measure, and also the diameter of the network. Some of them are very long here, but long with high clustering coefficient, long with, for example, a bigger average path length, or long with a shorter average path length. So we try to build network which follows different characteristics here. And also there are some setups that we need to follow. For example, aspiration value, which determine the accepted desired outcome out of the played game for agents. We actually perform sensitivity analysis on this parameter, but this wasn't the main contribution of our paper. There are some researchers, I think I have included the link, that they basically performed the sensitivity analysis, and they figured that out, that probably, for example, if you go on 4 as the aspiration value, you can expect to come up with a population which with less you know, with less percentage of cooperative behavior, and the 2 and 3 are those which are appealing. So we also followed the previous works in this area. But anyway, the range, I've mentioned it here. Initial propensity value, which shows the percentage of population which will follow cooperative behavior at the beginning of the simulation. Again, I assign a range, but according to the literature, for example, we're not really interested in 0.5 and 0.8, because if we start the simulation and a large percentage of the population follow a cooperative strategy, people can claim that, yeah, that's why you ended up with such and such result, because a large number of population followed a cooperative strategy at the beginning. So usually this value should be small, and we decided to choose the value 0.3, like 30% of the population is following the cooperative strategy, and the rest will do defection, but they will learn. And at any time, if there is any dissatisfaction or satisfaction, then this propensity will change, and the amount of change is 0.1, so that we go up and down. There are partner selection strategies. We have 5 partner selection strategies based on reinforcement learning algorithm, bandit algorithm, which are selecting the partners differently. And we ran the simulation for 5,000 steps. So coming to the experimental setup, as I mentioned, we tested some algorithms. For example, we also tested EXP, but we don't mention it here because we found out at the end that the performance was almost similar to random. We could justify why. And I think due to the limited number of pages in the paper, we decided to remove those experiments, but we will probably include them in the extended version of the work. So let's just briefly say what are these bandit algorithms and how they work. Let's say random selection of partners, we pick this strategy as the base. So that means while we're doing the simulation, each agent wants to pick a partner and they decide to do it randomly. So if they are doing it randomly, they have no idea who is good, who is bad, they just do it randomly, and we will consider it as a base model. So now we have epsilon greedy, epsilon decreasing, epsilon first, and upper confidence bound interval. In epsilon greedy approach, we say that the agents will try to do exploration and exploitation. So exploration in the sense that they don't know anything about the environment, they try to learn, and if they learn something, they keep exploiting it. So if they find out that one of their neighbors is doing better than the others, they become greedy and they keep interacting with that specific agent. So there is a chance that we will start in local optimum, and well, but that's something which is already accepted in the literature. So we brought it here as another style or form of partner selection strategy. Epsilon decreasing approach. So we say with certain probability the agents will explore and also they exploit, but this exploration should decrease based on time. And the reason is, the other papers, they argued that, well, the more you know about your environment, obviously the more information you will have about your partners. So if that's the case, why more exploration? So exploration should decay over time and we should do more exploitation. Epsilon first approach has another argument. So we say, you know what, we don't know anything about the environment, so let's randomly try to pick a partner for a period of time at the beginning of the simulation. So then we have an understanding of what's going on around us, and after that we keep doing exploitation. And well, we don't know whether they're good or bad, we just want to test them. And finally, upper confidence bound algorithm, which was very successful in our case, we are trying to do exploration and exploitation, but the whole idea of this algorithm is that we are trying to create a confidence bound around each option that we have. Well, this confidence bound depends, has a direct relationship with the number of time a partner will be selected. If you keep selecting a partner and your partner is giving you a good outcome, the outcome of this or benefit, then you have probably the good average payoff, but the confidence bound for this option will be very low because you keep interacting with this person and this person always play the same strategy. So in total, the average will be good, but the confidence bound will be smaller. So if this is the case, you can always use this partner for exploitation. But for exploration, the idea of the algorithm is, let's look at the other options that we have and let's see which of them has the highest confidence bound interval. So if there is a high confidence bound, then optimistically this algorithm assumes that in the long run you can get a better benefit by interacting with this partner. And that's because the algorithm assumes you don't know this partner very well, so you should do more to learn more about this. And if you keep doing more and then the average payoff is low, then probably that's something that you should put aside and keep interacting with other partners. Okay, so now experimental result. How much time do I have, Karim?
You have another 4 minutes.
Wow. Okay. So I'm trying to be quick here. So the first
All
part
right.
is that, yeah, we have initial propensity value and aspiration value. As I mentioned, sensitivity analysis is needed for combination of these two, but that wasn't the goal of our paper. This was something which was done in the literature. And the literature also, we also observed the same result by previous finding. As initial propensity value basically will have a direct effect on the peak of uh, percentage of cooperation. If you set initial propensity value to a high value, at the beginning of the simulation, you see a peak, and after that, you will see the decline in the percentage of cooperation. And aspiration value, if you pick it as a high value, for example, 4, which depends on the payoff of the prisoner's dilemma game, you should expect that the agents show more tendency towards defection. And this is actually what we also observed. So we reached the society that that the percentage of cooperation was just mutual cooperation was just 10%. But 2 and 3 is good. So we started at 90%, but the percentage of mutual cooperation became 45%. And at that time, the question was how we can improve it from 45%, how we can go up. And that was why we introduced the partner selection strategies to see how we can change this 45% to something bigger. So as you can see, we have 5 partner selection strategy, and we have 9 networks, in total 45 observation. And this image in particular, this plot shows that UCB in general is able to deliver us a higher percentage of mutual cooperation in the population, which we will see in the next slide, but in a shorter time. So if the simulation time is 5,000, UCB is able to deliver a population with higher level of cooperation in shorter time, something like 1,000. The next rank goes to epsilon first, and for the epsilon greedy and random, you see we are on the 5,000 limit, and the percentage of cooperation, we will see that it's not very good. So now let's look at the median value and interquartile range as measure of variability or dispersion. For the epsilon greedy and random, you see here the percentage of cooperation is not going high more than 70%. But for UCB, we already we are able to achieve a mutual cooperation of 95%. That, considering the interquartile range with 5, for example, here in case of SCM, SCM here is something around 95. So 95 plus 5 is like we are becoming very close to having a population which is 100% cooperative. And this was something appealing. But we also had another observation here that there is something special about SCM, because SCM, it seems it's a kind of network that is very successful, right? With the right partner selection strategy, with the right network structure, we are able to deliver a very highly cooperative society. But what is special about SCM? So we try to look into the networking characteristics, and what you can see here, for example, when you look at the node degree, SCM follows a symmetry here in terms of node degree connectivity with the others. But then when you look at SW, like our small world network, you also follow a symmetry in the observation here as well. So this is not the main reason. So symmetry in the number of connection is not the main reason. But what is the main reason? So we try to look at the relative eccentricity distribution among the network, and we identified that, well, basically, we observed a very long, shortest path from any node in this SCM network to the other node. So if you remember, SCM had a very large diameter here, 20, But you know, that can be different across all the nodes, this longest path when it comes to calculating the shorter distance. But in general, we see a trend for this small world network, and for SCM, the trend is very different. The distribution of eccentric values are different than other types of network. So this gave us the motivation to look further into other network characteristics, so that we compare what's going on, what's the difference between our small world network or SCM. And we identify that in terms of closeness centrality, yeah, so the eccentricity distribution shows that there's a very long distance between the nodes in the network. But what is special is that when we compare these two networks, there is a in the box plot of the clustering coefficient for SCM, we see a wider range of clustering value comparing to the small world network here, which the range is almost fixed. So there is no box plot here because everybody follows the same. So this range gave us the idea that in order for a network to produce higher level of mutual cooperation, we should have the long distance among the network members, but also we should observe a higher level of clustering coefficient among network members. So these were the conclusions. So if you look at it, I just basically summarized everything. In order to having a successful spread of cooperative behavior, we need to create a network among the members which gives us heterogeneity in terms of distance to others, as well as clustering coefficient. And basically UCB gave us this higher performing partner selection strategy. Well, thank you so much. I hope that I've been considering that 2 or 3 minutes that we were late.
No worries.
If you have any question, I will be happy to. I will be happy to discuss it with you guys.
Thank you, Somayeh. Any question? We have time. Who wants to start? Yeah, please go ahead.
Me. I can't vote. Is there a way to take the theoretical results? I mean, now that we know what algorithm would work and will bring the population to collaboration, is there a way to take this into practice to make people behave in a way?
Well, that's a good question, because you know what? This when I showed you these networks, nobody asked how do they look like. So, and you know what, the reason is, for us, when we are in the networking theory, we care more about these values here, right? So we say how these networks are different in terms of this measure, and this measure. But I think what Orna is asking here is very interesting. So now I want to put this one into practice, right? I want to foster the emergence of cooperation among a group. What should I do? So I think these two is telling you a hint what you should do. So it means that, imagine we are setting up a division or a group, and we are bringing some people together. There is a group, for example, let's say computer science department. So computer science department, there is a group, they are working on, let's say, networks. There is another group, they work on artificial intelligence. There is another group, they work on health rate. Like other divisions, right? So, and each of them, we have a supervisor, and the supervisor has a team. So this supervisor is bringing 10 people together. So the result of this research is saying, in order for the computer department to be successful in terms of promoting the cooperative behavior, the groups, they should ask the people to cluster together. work together. So we need those clusters. But in addition to those clusters and connectivity between the cluster, we better don't bring them very, very close. So this means if you suddenly try to create a small world network in that division, and you start creating random links from artificial intelligence department to the networking department, from networking department to another division, this will not work, because the presence of shortcuts will shrink this average shortest path length. So we are observing a network which doesn't have a long diameter. So that was what happened when we look at a small world network here in my simulation. So coming back to your question, if we want to apply the result into practice, probably the people who are in the I don't know whether it's the job of HR or it's the job of the group leader or someone who's managing the division. They should have this in mind that yes, so the network setting, the way people are connected from where to where, is very important.
Okay.
And well, there is one more, I think, aspect. If we not just look at this, not just look at the network structure, I think when it comes to UCB, the upper confidence bound interval, probably we need more realistic. That algorithm performed better than the others, I think, and I believe due to a reason. I think upper confidence bound interval is very close to the way a human also will think or judge. So 10 people, I know that who's my favorite partner, but the rest, I don't know. I'm trying to bet. And the amount of bet that I'm putting on the rest of the population depends on the confidence interval, or it's better to say how sure I am about them. So, and you know, the more I interact, the better I know, and the better I can judge who is doing good or bad. So I think this is more probably a suggestion. And I think there was one more slide that I forgot in case anybody is interested. I'm not sure, probably your for your group. So I considered the monoplex network. So this was just a one-layer network, but probably an extension of this research would be considering a multiplex network in which people are located on different, they're connected with each other, but with different contexts. And context of a layer, information from one layer may impact, you know, the connectivity or the interaction on another layer. So this is something we can do. And yeah, and also multi-layer networks probably good for the people who are in the cloud computing area. So it's not just about humans, but also some network which shows some like different entities exist on different layers, and probably that has something like a policy. So we have a layer of organizational policy, and organizational policy will rule how people impact on another layer, but there is still another layer like friendship or trust network which may impact this process. Well, thank you so much for the like the time that you give to me and being patient with me.
Thank you, Somayeh. Thank you. I would suggest that if you have further questions to Somayeh, could you please contact her directly, or there will be a chat room later on, and certainly in the next couple of days. Thank you, Somayeh. Our next speaker, third presentation in this.
Stop record, start record.
Yes, please. Yes. Oh, no. Yes, please. Yes, me. Of course. Yeah. I need a process here. Let me just stop the recording.